here we have question number 1. It says, determine whether the following compounds are electrolytes or non-electrolytes. If it is an electrolyte, write the equation for the dissociation in water. Determine how many ions are formed. So they want us to determine whether or not they're electrolytes. And also they want us to figure out how many ions. Alright? So first of all, what is an electrolyte? And electrolytes are formed from solutes that are soluble ionic compounds. So simply put, electrolytes are ions. Whether they're cations, positively charged ions, or anions, negatively charged ions, those are going to be electrolytes. And then we can ask ourselves, how can they dissolve in water? So I have over here table salt. We've discussed table salt a lot throughout the semester, and we're going to be using this, since we know that it's ionic, to figure out why does it dissolve in water. So dissolve is to come apart, right? So every time that we have an ionic compound, is going to be dissociating, aka coming apart. So let's go ahead and do that with this sodium chloride. Alright, so I just wrote them apart. And then, why does it dissociate in water? Well, I'm going to go ahead and draw water over here so that that makes more sense. And we know that the oxygen has a partially negative sign because we know that oxygen is more electronegative, and therefore we're going to have electrons more attracted to it. And hydrogen is partially positive. So whenever we throw in salt in water, the reason why it dissociates is because this positive sign over here is going to be interacting with this partially negative sign of oxygen. And for chlorine over here, we're going to have this negative sign right here interacting with the partially positive sign of the hydrogen. So when we actually look at this molecule, the reason why it dissociates is because they interact. And we're going to have Na, because of its positive charge interacting with the partially negative sign of oxygen. And we're going to have chlorine over here, negative charge, right? It's an anion, so it's going to be interacting with the positive charge of hydrogen. So over here, we just have to write the dissociation. So when it dissociates in water, we're going to have Na plus and Cl negative, and we just have 1 and 2, a total of 2 ions, right? 1 and 1 equals to 2 ions. Right. And you don't have to write the 1 over here. I just did that so that you can see where the 2 is coming from. So now let's go ahead and look at this second example over here. We have potassium sulfide. So we want to write the dissociation in water. And again, all that we're doing is writing them apart with their charges. So we know that this is the final chemical formula right here. So we're going to be going one step back to figure out what the charges are. And in order to do that, I'm going to write them separate, and these two right here I'm going to go up and across to symbolize the charge of sulfide, and same thing over here, up and across. There's nothing, so it is a 1. And also we know that this is a +1 because it's in the first group of the periodic table, and we know that this right here is a -2 because this is one of the ones that you're supposed to memorize. So all that I'm going to be doing then is writing them separate over here. All right. And Notice how you have 2 potassiums, right? There's a 2 right here for the potassium. So you have 2 potassiums, and therefore I'm going to be writing that over here because we have 2 potassiums and then just one sulfide. So if you add these 2 together, right, you have 2 plus 1, so you have a total of 3 ions for that particular example. Then we have ammonium phosphate right here, and the very first thing that we have to figure out is whether or not it is an electrolyte. And we know, because we were supposed to memorize ammonium and phosphate, that they are electrolytes because they're ions, right? Ammonium and phosphate are polyatomic ions. They are charged. So first off, let's go ahead and write them out separate. And let's figure out what the charges are. So this number right here, I'm going to go up and across. And this number right here, well, there's nothing, so that means that it's just 1. I'm going to go up and across. So remember, you write the cation first, so the positively charged first, and then the anion second. Okay? Now that we figure out the charges, I'm just going to go ahead and write down the dissociation with the charges that we just figured out. Okay, after you do that, now you have to figure out how many ions. So the way to do this is to look at the chemical formula, and you figure out how many of each there are by looking at ammonium first. There are 3. So you're gonna write that here. And then you're looking at phosphate. We just have 1. You don't have to write it, but again, I'm writing it so that it's easier for you to know where I'm coming out with the numbers. So then we're just gonna go ahead and add these 2 ions. So 3 plus 1, we have a total of 4 ions. Next, we're looking at ethanol. So again, first thing, we have to figure out whether or not it's going to be an electrolyte. So you might look at this and think, well, I know that I memorized OH as hydroxide, so yeah, this is going to be an electrolyte. But if you were to draw this out, you're going to see that OH is not acting as an ion. And for that reason, no, this is not going to be an electrolyte. And we can leave it alone. Then we have over here aluminum nitrate. So the very first thing to do would be to figure out whether or not it's an electrolyte. And we know that aluminum and nitrate are charged. So yes, it's going to be an electrolyte. And let me go ahead and write them separate to figure out what the charges are. So I'm going to take this number and go up and across. And this number, there's none, so that means it's a 1. And go up and across. And that's going to be the charges. So we have +3 and -1. Okay, now that we figure out what the charges are, let's go ahead and write the dissociation. And I'm going to be writing them here separate with the charges that I already figured out. Then you have to figure out how many ions there are. So looking over here at the chemical equation or chemical formula, we have just 1 aluminum and we have 3 nitrate. Now I'm going to go ahead and add these 2 numbers. So we have 1 plus 3, we have a total of 4 ions. Alright guys, so on to the next question. It says colloidal suspensions contain particles, colloids, that are between 1 to 200 nanometers in size. Colloidal particles are large molecules such as proteins, groups of molecules, or ions. These colloidal particles are small enough to pass through filters, but too large to pass through semi-permeable membranes. Each of the following mixtures is placed in a dialysing bag and immersed in distilled water. Which substances will be found outside the bag in distilled water? So let's go ahead and draw what's happening right here. We have I have a beaker here. Alright, don't judge my drawing. And in this beaker, we're going to have a dialyzing bag. And it's going to be submerged, like it says over here, in distilled water. Okay? So, we know that colloids cannot pass through semi-permeable membranes, and a dialyzing bag is a semi-permeable membrane, which means that inside this dialyzing bag, we're going to be finding colloids. So let's get started. Letter A, potassium chloride solution and glucose solution. So because they're not telling us that it's a colloid and they're not giving us a size in specific, we can assume that it's small enough that it's not going to be in the semi-permeable membrane, but is going to be able to diffuse out. So this is going to be outside. Then we have albumin solution. It's telling us right here that it's a colloid. And looking at over here our figure, we know that colloids are inside the bag. Then it says a starch solution, colloid, and a potassium chloride solution and glucose solution. So over here again, they're telling us the starch solution is a colloid. So this is going to be inside. And the potassium chloride solution and glucose is going to be outside. Then it says urea solution and sodium chloride solution. Again, they're not telling us the size in specific, so we're going to make the same assumption that we made for letter A, that it's not going to be in the bag, but it's going to diffuse out. So this is going to be on the outside. The big thing here was to identify that colloids are not able to pass through semi-permeable membranes, but they can pass through filters. And saying that we have a dialyzing bag, you can ask yourself, is that a filter or is that a semi-permeable membrane? And it was a semi-permeable membrane. So for that reason, we know that colloids are going to be inside the bag. The next question says, a solution contains 3.5 grams per liter of sodium bicarbonate. Express this in percent mass over volume. So this mass over volume right here is a unit of concentration, and they want us to know that percent of unit of concentration. So you're going to have to know this equation right here. Grams of solute over milliliters of solution times 100%. Okay? They're telling us that we have 3.5 grams per liter of that particular solution. This right here is the same as this. Okay? 3.5 grams per 1 liter. Okay, now looking over here at the formula that we have to use, let's see if there's anything that we can do. So we have grams, so that's already there, great. Then we need milliliters of solution. Well, we happen to have how many liters, right? We just have 1 liter of that solution. And because we know that we can convert liters to milliliters, then we have everything that we need. We know that there are 1,000 milliliters in just 1 liter. So let's just go ahead and plug everything that we know into the equation. (3.5 grams over 1,000 milliliters of solution times 100%, very important not to forget the 100%, equals, you're gonna go ahead and plug everything into your calculator, and your final answer is going to be 0.35%. Okay, now let's check the significant figures. We have 3.5, so that's 2 sig figs, and over here we also have 2 significant figures, so this is going to be my final answer. The following question is asking us, how many grams of glucose are needed to prepare 200 milliliters of a 5.2% MV solution? So once again, we're going to have to use this equation. Grams of solute over milliliters of solution times 100%. Then looking at this question, they're asking us for grams, right? And we have 200 milliliters that we're able to plug in here, and 5.2% that we're able to plug in here. So let's go ahead and do that. 5.2% equals grams of solute, which is what we're looking for, over the 200 milliliters, and don't forget, times 100%. Now, since we want to isolate these grams, now we're just going to be using some algebra. Let's start out with this 100 right here. It's being multiplied, so to get rid of it, I have to divide by 100%. Whatever I do on this side of the equation, I have to do on this side as well. So this divided by 100%. And then I have 200 over here. Again, I'm trying to isolate grams, so because it's being divided right now, I have to multiply times 200 milliliters. This is able to cross out this over here, and whatever I do on this side, I have to do on this side. So this times 200 milliliters. So now we've isolated it. Really, what we have is grams equals 5.2 times 200 over 100%. Okay, now you're going to go ahead and plug this into your calculator, and your final answer is going to be 10.4 grams. Now let's look at significant figures. We have 3 sig figs there, 2 sig figs here, so that means that my final answer should have 2 significant figures. So we're gonna stop right here. Look whether or not you have to round. We do not. So my final answer will be 10 decimal, right? Because without that decimal, it wouldn't be 2 sig figs, and your units. The next question says, a doctor orders 100 milliliters of 2% MV ibuprofen. If you have 8% MV ibuprofen on hand, how many milliliters do you need? So we want milliliters, all right? So with this type of questions, every time that you have one solution and they're asking you for another solution, think about C1 V1 equals C2 V2, okay? Now that you know that this is the equation that you're going to have to use, or the formula, we can go ahead and start plugging in some numbers. So it says a doctor orders this, right? This solution. So that means that that's our end result, right? So that's going to be on this side. So 2.00% MV and 100 milliliters, and over here we know the concentration, what we're starting out with, 8.00% MV, but we don't know the volume, right? actually. Now that you've figured this out, it just comes down to solving it. Some algebra again. So we want to go ahead and isolate this volume. So this is being multiplied right now, and therefore I'm going to go ahead and divide it to get rid of it. Divide 8. Whatever I do on this side, I have to do on this side. 8.00% MV. All right. So you're going to go ahead and plug this into your calculator. And your final answer is going to be 25 milliliters. You check significant figures. So you have 3, 3, 3, which means that your final answer should also have 3 significant figures. So 25.0 milliliters, and we are done. The next question is asking us, what is the concentration in parts per thousand if 80.4 grams of calcium chloride is dissolved in 250 milliliters of water? And then it says, what is the density of water? So every time that they're asking us about parts per thousand or parts per million, we have to be familiar with this equation right here. For parts per thousand, you have to know grams of solute over grams of solution times 4,000, 1,000. If it's parts per million, this is going to be the same. Grams of solute over grams of solution. But instead of 1,000, you're going to multiply it by a million, which is this. But since they're asking us about parts per thousand, let's go ahead and focus on this. First off, if I want to break this even farther, just know that grams of solution is the same thing as grams of solute plus grams of solvent. So now let's go ahead and look at this problem and see what we can go ahead and plug in. So for parts per thousand, which is what we want, grams of solute, here's our solute, 80.4 grams of calcium chloride, and we can then go ahead and add that here, 80.4 grams. But as you can see, we're missing the grams of solvent. They're telling us the milliliters of the solvent. So how can we go ahead and figure out the grams? So this is a hint right here, right? When it says, what is the density of the water? That's a hint. So the density of water is 1 grams per milliliter, okay? So since we know this, then you can go ahead and solve for the grams. So since the density is 1.00 grams over volume, milliliters, the milliliters are 250, so I can go ahead and plug that in. And you can go ahead and solve for grams. So again, what did we do? We know that density is grams over volume, and for water is 1 gram over 1 milliliter, okay? So again, since I know that it's mass over volume, let me even write that here, grams over volume, then I went ahead and I wrote the density equals grams, we don't know, right? That's what we're looking for, over milliliters is given to us. So I went ahead and I plugged that in here. Now you can go ahead and solve for grams. So you're going to isolate the grams by multiplying 25 250 milliliters, so that this gets crossed out. Whatever I do on this side, I have to do on this side. So times 250 milliliters, and this is simple enough, right? You don't even have to plug this into the calculator, because 250 times 1 is going to equal 250 grams. But as you can see, right, the milliliters get crossed out and you come out with grams. Great, because that's what we needed. The grams of the solvent, which is water. So I'm going to go ahead and plug that in here. 250 grams. And what we do not want to forget is the 1000. Now you're going to go ahead and plug this into your calculator, and the answer is going to be 243.3 parts per thousand. Now let's check the significant figures. We have 3, we have 4, so our final answer should have 3 as well. So I'm going to go ahead and stop right there, see if I have to round. I don't, so my final answer is 243 parts per thousand. Okay guys, here's the next question, and it says, polychlorinated biphenyls are a group of 209 different chemicals which share a common structure but vary in the number of attached chlorine atoms. An estimated 1.3 million pounds of different types of polychlorinated biphenyls were dumped into the Hudson River by General Electric from 1946 until 1977, when they were banned. The International Treaty on Persistent Organic Pollutants, drafted by 122 nations in Johannesburg in December 2000, targeted polychlorinated biphenyls as one of the dirty dozen chemicals to be phased out worldwide. Polychlorinated biphenyls increase rates of certain cancers, cause development effects, and disrupt hormone function. Then, after all of that information, they ask us, or they tell us, 1 parts per million is equal to 1 grams of solute in 10 to the 6 grams, so 1 million grams of solution. Calculate the mass of solute of PCB, so polychlorinated biphenyls, in a 65 kilogram person if the concentration is 4 parts per million. So again, like we discussed in the previous question, if we have parts per million, the equation that we have to know is grams of solute over grams of solution times 1 million. Okay, now let's see what we can go ahead and plug in. We have the parts per million, so we can go ahead and plug that in here. We also have the grams of the solution. They're actually giving us 65 kilograms of the person. The person is the solution in this example, because it has the solute and the solvent, right, within that person's system. So because we have kilograms and the equation says for us to have grams, we will have to change it in order to comply. So we have to go from kilograms to grams. So that's gonna give us 65,000 grams of the solution times 10 to the 6. And what we are looking for is the grams of the solute. So notice how I could have just go ahead and figured this out from this very last sentence. So after all of this information, although you might consider it interesting and informative, we didn't really need to know any of this for us to come out with this question. So this is important to understand when it comes to exams. Every minute is going to be valuable. So when it comes to questions like this, when they're giving you all of this information and then you see a question, I will first go ahead and look at the question before even reading this paragraph out to see if you even need to read it, because you might not need to. But anyways, after you do this, you're going to go ahead and solve for grams of the solute. So in order to do that, I'm going to isolate it. So I have 65,000 here. It's being divided, so I'm going to go ahead and multiply it so that I can cross that out. Whatever I do on this side, I also have to do on this side. So 65,000 grams. And I have 1 million. So it's being multiplied right now, so I have to divide it, right? Just algebra. Whatever I do on that side, I have to do on this side. 6. And now we have isolated it. I'm going to go ahead and write it so that it makes, or I guess so that it's a little bit clear to understand. So we have grams of the solute equals 65,000 grams times 4 parts per million divided by 10 to the 6. And our final answer is 0.26 grams. Now, let's look at significant figures. We have 1 and 2. So our final answer should also have one significant figure. So I will go ahead and stop right here. Figure out if you have to round. We do. So our final answer then is 0.3 grams. The following question says, calculate the molarity of a 325 milliliter solution that contains 6.7 grams of sodium chloride. So they're asking us to find out the molarity. All right, so that means that you have to know the equation. Molarity equals moles over liters. Then let's go ahead and see our givens. Our givens are 325 milliliters and 6.7 grams of sodium chloride. So there's really nothing that we can just go ahead and plug in, but we have the volume, right? Although it has to be in liters, we have milliliters, and we know how to go from milliliters to liters. So that would be 0.325 liters. And we can just go ahead and plug that in. Now, for grams, we need moles, but we know how to go from grams to moles. We're going to be using the molar mass. What we want is going to go on the top. What I want to get rid of is going to go at the bottom. And I want the molar mass of sodium chloride, which is going to be 58.44. This is going to be able to get rid of my grams, and I can come out with moles. My moles are going to be 0.114675017 moles, right? And this number right here, I can go ahead and plug it in. And you want to take the whole number. You don't want to round until the very end. So now that I have these two numbers, let's go ahead and plug them in. We have 0.114647517 moles over 0.325 liters. You're going to plug this into your calculator, and your answer is going to be 0.3527615 blah 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 moles over liters. Okay, now let's look at the significant figures. We have 3 versus 2, which means that our final answer should have 2. You're gonna stop right there, and that means that our final answer is 0.35 moles over liters, which is the same as 0.35 big M, right? The big M stands for moles over liters. The next question is asking, how many grams of glucose are needed to make 500 milliliters of a 0.125 molarity glucose solution? So first off, identify what they are asking. They're asking us for grams of glucose, so we want grams as our final unit. And let's just write down all of our givens. So we have 0.125 molarity, which is the same as 0.125 0.125 moles over liter. And then we have 500 milliliters. So again, we want to end up with grams, and we have these units right here in place. So looking over here, we can see moles, and we know how to go from moles to grams. However, this is not just moles, right? This is moles over liters. So we will have to find a way to get rid of these liters right here so that we can come out with moles. So what do you have to do to this fraction to cross out these liters? You have to multiply, right? You have to multiply these by liters. So you might ask, well, by what liters? Well, they're giving us 500 milliliters. So we know how we can easily change from milliliters to liters. So let's go ahead and do that. This is the same as 0.500 liters. So now I can use this and plug that in here, or write this up here, so that I can cross out liters. By crossing out liters, I come out with moles. So you can plug this into your calculator, and your answer is going to be 0.0625 moles. Now, we are trying to end up with grams. So I'm going to take this 0.0625 moles, and we're going to be using the molar mass of glucose to come out with the grams. So what I want is going to go at the top. What I want to get rid of is going to go at the bottom, so I can cross out moles and I can end up with grams. And the molar mass of glucose is going to be 180.16. So you're going to plug this into your calculator, and your final answer is going to be 11.26 grams. But let's not forget about significant figures. We have 3 suffix here, we have 3 here, so our final answer should also have 3. Let's stop right there. Do we have to round? Yes, we do. So our final answer is 11.3 grams of glucose. The following question says, the lab manager has 150 milliliters of a 12.3 milligrams per milliliter solution and dilutes it to a final volume of 680 milliliters. What is the concentration of the diluted solution? So every time that we have dilution taking place, you're going to be using this equation. C1V1 equals C2V2. The C stands for concentration and the V stands for volume. On the left side right here, the C1V1 is going to be before the dilution, and the C2V2 is going to be after the dilution. So now let's go ahead and see if we can plug anything in. We have this solution, so this is going to be on the left side, right before the dilution, and we have 12.3 milligrams per milliliter, and we have 115 milliliters. C2 we do not know. The final volume they're telling us is 680 milliliters. Something important here is to make sure that the volume has the same units. So we have milliliters here, we are good. If we had been given 2 concentrations and we had to find out the volume, it's also important to make sure that the concentration has the same units. So back to this, the volume has the same units, so we're good there. Here's our concentration, and it's important to know that our final concentration is going to have the same units as the initial concentration, okay? So now I'm simply going to go ahead and solve for C2. We are multiplying right here 680, so in order to get rid of that, I'm going to go ahead and divide. Whatever I do on this side, I have to do on this side. 680 milliliters. This is going to get rid of my milliliters here, and I'm going to be able to end up with these units. for my concentration. So now you're going to go ahead and plug this into your calculator. So now I'm gonna go ahead and write it again just so that it's clear. We have concentration 2, or final concentration, equals to 2.3 milligrams per milliliter times 115 milliliters divided by 680 milliliters. Your answer is going to be 2.08 milligrams per milliliters, which were our units for the concentration. So now let's look at significant figures. We have 3, 3, 3. So our final answer should also have 3, and we do. So we're done. Here we have our final question, and it says, a student has a bottle labeled 0.750% M/V glucose solution. The bottle contains exactly 25.0 milliliters. How much water must the student add to make the glucose concentration become 0.100% M/V? So let's think of what's happening here. We have one bottle. (0.750%) with 25.0 milliliters. We want to end up with a concentration of 0.100%. Notice how your concentration is getting lower, so you are diluting. Okay? We don't know what V2 is going to be. So again, our concentration is getting lower, so that means that we're diluting. We know that if we are diluting, we're going to be using C1 V1 equals C2 V2. So let's take it one step at a time and go ahead and add what we know. So what we're starting out with is 0.750% MV. Volume is 25.0 milliliters. C2 we know, which is 0.100%, and V2 we do not know. So now let's go ahead and solve for V2. We want to isolate V2, which means we want to get rid of this. It's being multiplied right now, so to get rid of it, I have to divide. Let's not forget my units. So I'm gonna be able to get rid of it here. Whatever I do on this side, I have to do it on this side. Notice how my units here, percent MB, get crossed out, and I'm left over with milliliters, which is a unit of volume, which is what we wanted. So let's go ahead and write everything out again so that it's easier to observe what we're doing. So V2 is the same as 0.750% MV times 25.0 milliliters over 0.100% MV. And again, something that we wanted to make sure of is that the units of concentration were the same. Okay, so those were the same, we were good. And our units of volume are now going to end up being ml, since the percent MV gets crossed out. So you're going to be plugging this into your calculator, and the answer is going to be 187.5, okay, milliliters. So this V2 right here is 187.5 milliliters. But they're asking us, how much water must the student add? Okay, they're asking us, how much water must the student add? You started out with this volume right here, and you're finishing out with this volume right here. So in order to find out how much the student added to end up with this volume, we will have to figure out the difference. So we have 187.5 milliliters V2, right? Minus, or V1, which is 25.0 milliliters. And this is going to give us the added volume. Okay, so plug this into your calculator and your answer is going to be 162.5 milliliters. Now let's check the significant figures. We have 3, we have 3, we have 3, so our final answer should also have 3. So we have to stop right here. Do we have to round? Yes, we do. So our final answer is 163 milliliters added. So the student added 163 milliliters to the initial bottle to come out with the desired concentration.